Alright, so let's talk about the Pascal triangle. The Pascal triangle, as I did a video on it before, you construct it by starting with 1, 1, 1. And then what you do is you put ones always at the end, and then in between two numbers, you're going to add them up. So when you add these two numbers, you get 3. And then you put ones at the end, and you continue like that. And what I explained in the other video that I have on the Pascal triangle is that if you wanted to do a plus b, say to the fourth, which is this row, the numbers go 0, n equals 1, n equals, am I outside? Maybe. N equals 3, and n equals 4. And you continue like that all the way, however many you want to do. And the way you do it is like this. You grab the coefficients 1, 4, 6, 4, 1, and the first term you're going to do 1 times a to the fourth. That's your first term. Then you're going to do plus 4. You're going to lower the degree of a by 1, which is going to be a cubed, and you're going to increase the degree of b by 1. There was nothing, so you put b. Then you go to 6. Can I fit it there? Yes. And you're going to lower the degree of a by 1. And you're going to increase the degree of b by 1. Keep going down. The next coefficient is 4. You're going to lower the degree of a by 1 and increase the degree of b by 1. And lastly, you get to the very last one where you lower the degree of the coefficient is 1, lower the degree of a by 1, increase by b by 1. And you get that. So those coefficients are given by the Pascal triangle. But you also know, or maybe you don't, that a plus b to the n can be written in terms of the binomial theorem, which tells you that it's going to be the sum from k equals 0 to n of n choose k, a to the k, b to the n minus k. But if we expand this for 4, so at n equals to 4, let me change this marker. I think it's going to get a little bit too light. I'll be right back. Let's try this one. About the same. So at n equals to 4, this would become just this sum here becomes k equals to 0. You get n choose 0. A to the power of 0, so just a. So just 0, a to 0, which is 1. And b to the power of n minus 0, so b to the n. So I'm kind of going backwards, but n was 4. I forgot about that, so let me change that. I'm going to write b to the 4. Then you would do and say 4 choose, when k is equal to 1, 4 choose 1. And then you get a to the power of 1, b to the n is 4, k is 1, so 4 minus 1, 3. And then you get 4 choose 2. And then you would have a squared, b squared. This is making a lot of noise. I don't like it. Then 4 choose 3. A cubed, b, plus 4 choose 4. A to the fourth. So now, from what we saw above, we have the same expression, but notice that this should be equal to a 1. This should be equal to a 4. This should be equal to a 6. And you can check that those numbers are right. But what that means is that then, whenever you go and do the n equals n, if you will, you're going to have n choose 0 in the Pascal triangle, n choose 1, and you're going to have all those all the way out to n choose n minus 1, and all the way down to 1, which is going to be n choose n. So the entries on the Pascal triangle should be equal to the binomial or the choose function, or the binomial coefficients, or the coefficients in the binomial theorem, if you will. Alright, so let's go ahead and and show that. Let's try to show that this formula works. And if this formula works, really what I'm saying is that when I'm doing n minus 1, actually let me redraw what I want, because I want the ith term. I don't want the one term, I want the ith term. So somewhere in the middle, if I have n choose I, then what I should have to establish then is that n minus 1 choose I minus 1, and then n minus 1 choose I plus 1 should give me this right here. So when I add them together, should give me that. So let's go ahead and check that out. All right, looking at this, I made a mistake. It should be this. Because you're going starting 0, in this case say 0, 1, and 2, 3, all the way to I. So if you wanted to do, for example, the one below would be n plus 1, choose, in this case would be 1, because the 0 is starting here. So you're going to do the 1 minus 1 and then just 1. So I was skipping one step. I don't need to. So we need to evaluate that. And so if you remember your formula for n choose k, which I probably should have mentioned earlier, I may just splice the video, put it before, bring it back in. So n choose k is just going to be n factorial over k factorial, n minus k factorial. And in this case then, your n minus 1 choose I minus 1 plus n minus 1 choose I is going to be equal to n minus 1 factorial over I minus 1 factorial n minus 1 minus I minus 1 factorial. That was long. Plus, and this marker is letting me down, so I'm going to get another one. Plus, now this term, n minus 1 factorial over I factorial n minus 1 minus I factorial. So now it's a matter of seeing what all we have. For example, we have a common factor n minus 1 factorial. And now what I have to see is which is the smallest of all these numbers. Maybe I should write this one out as well. So 1 over 1 minus, or I minus 1 factorial. And then times, I'm debating there with my space. When I have n minus 1 minus negative 1 is n minus, is going to be negative 1 minus negative 1 is 0, and I get n minus I. And then the other one, I just get a 1 over I factorial. Am I fitting there? Yes. And then n minus I minus 1 factorial. So I need to move over here and finish this calculation, and I think that's where we're going to wrap the video up. All right, let me go ahead and erase real quick. So what do we have? We have an n minus 1 factorial. And then when I multiply, I'm going to grab the smallest of each one of them. Actually, the largest of each one of them. So for example, I'm going to grab the I factorial for this one, because I minus 1 is smaller than I. And then I'm going to grab the n minus I factorial. And so what am I missing here to make this work? I need an I over I. So I get I factorial in the denominator. So I just get an I for this one. And what I'm missing for this one, I'm missing an n minus I multiplied, an n minus I multiplied in the denominator, or dividing by, which gives me the n minus I factorial. So n minus I, and that gives me n minus 1 factorial, n, that's going to be n factorial right there, I factorial, n minus I factorial, which is n factorial over this, which is n choose I, as we had advertised. So by doing an inductive argument, we show that the way we constructed our Pascal triangle actually gives us every binomial coefficient in the rows of the Pascal triangle. So that's a fun way of connecting the triangular number, the Pascal triangle, and a few combinatorial proofs. So we went on a little tangent, but today was just for fun. So there you go. Thank you for watching, and I'll see you in the next one.